Hello everyone, welcome to the next lecture. We are going to do some quick examples of some more applications of diodes. Okay, so we're gonna do a few of these quick examples in which we can use diodes in wave shaping circuits. And when I say wave shaping circuits, it isn't like we can make some cool like Apple waveforms out of it. The maximum wave, so we have kind of those limitations in terms of the wave shaping, is that we can build this kind of a clamping or clippers or limiter circuits. So we're going to do this example in which we will see how we can make clipper or limiter circuits. So the first thing is that what are clipper or limiter circuits? Clipper limiter, as the name suggests, they are going to limit the output values to a specific range, to a specific value, right? So clipper and limiter circuits will limit the outputs to specific positive and negative values. It won't allow it to become output to become more than a specific value or less than a specific value. Okay, for example, now we can see that, so this is the transfer characteristics. For example, over here, and just assume it to be a constant line here like this. For example, this is input voltage, this is output voltage, and this is, let's say, L positive, and this is say L negative. So what this waveform is showing me is that my output will be limited at a specific value, irrespective of how much I am increasing my input voltage. Beyond this point, my positive output cannot be more than VL positive, and my negative output cannot be less than L negative. So this is what the clipper or limited circuits will do. Right, for example, if I want to show you the corresponding waveform, for example, let's assume that we have the sinusoidal waveform. So the example would be, it is going to limit the positive and limit the negative. And we can specifically design our circuit such that we can define our L positive and L negative values ourselves. Now this specific example that I've shown, it is called as a double limiter, and double limiter is, it works on both positive and negative peaks of the input waveforms, right? So if we are limiting both, right? So if we are limiting both the positive and the negative peaks of the input waveform, it is called as a double limiter. Versus we also have single limiters, and I'm going to show you some of the examples which only limit one, either positive or negative peak of input waveform. If you are only limiting either the positive or the negative, then it's just called as a single limiter. Otherwise it is called as a double limiter, right? And these are also called as a clipping circuits, right? So also called as clipping circuits. As you can see, it is kind of clipping the waveform at this point and this point. All right, so let's do some examples. All right, so before we are going to build some circuits to do some examples, there's one more important thing. I'm going to kind of define the difference in between a hard limiter versus soft limiter. Okay, a hard limiter is an example that I have just shown. VI V0. So VI V0 is, for example, you have a sudden saturation value, right? So L negative, L positive. A soft limiter is something where there is a smooth transition in the saturation, right? For example, you go this, and then there is a smooth transition in the saturation, something like that, right? So soft limiter provides smooth transitions between linear and saturation regions, and slope of saturation region is greater than 0, right? Over here the slope is 0 and it is saturated exactly at the L positive value. However, for the soft limiters, we can see that there's kind of a smooth transition rather than this kind of an abrupt transition. Second, the slope is greater than 1, right? So it provides smooth transition in between linear and saturation region, and the slope is for the saturation region is greater than 0, but slightly greater than 0. All right, now let's do some examples of the limiter circuits. Okay, so in terms of examples, let's okay, so before we do an example, let me remind you the real model of a diode, right? So if you guys remember, we're gonna assume this model now. Sorry, this is the V, this is the I, right? So this will start here and then this, right? So we saw that typical values for which when it starts is around, when it starts conducting, it is around 0.7, and when the diode is fully conducting, it is around when the diode is fully conducting, it is around 0.7 volts, and when the diode will start to conduct, it is around 0.5 volts. So just remember these two kind of small differences. By the way, you will also realize that this is an important thing, because this will allow kind of a smooth transition in between the linear region and saturation region, right? It will allow smooth transition between linear and saturation regions. Okay, now let's draw some circuits. So we're going to do a couple of circuits here. First example is, suppose this is a resistor and here's a diode. This is the input voltage, here's the resistor, and here is the output voltage. Okay, so let's draw our VI characteristics. So we are going to see how our VI characteristics are going to look like, how our transfer characteristics are going to look like, being the relationship between V0 and VI. Now we will see, as VI is less than 0.5 volts, right? When my input voltage will be less than 0.5 volts, diode will be cut off. Diode will be off and open circuit. Since the diode will be off and open circuit, so this means that my V0 will be equals to VI. Okay, so approximately, let's say it is around 0.5, it is around 0.7, just putting down the values here. So for this, almost this entire region, for all the negative values of VI, it is going to remain linear, and this will continue. Okay, now as VI exceeds 0.5, it will start to conduct and become fully conducting at 0.7 volts, right? And at that point in time, And at this point in time, our output voltage become equals to 0.7 volts and will become constant. So at 0.5, it will start to conduct, and there will be a smooth transition in between 0.5 to 0.7, and then there will be a saturation. Okay. So we can, sorry, where did it go? Okay. So we can see that this transition is a smooth transition, and this is because of this characteristics of the VI characteristic of the diode. And we can see that it is limiting the voltage, which is equal to the potential drop across the diode. For example, if I would have connected two diodes in series, this would have limited or clipped the waveform at 1.4 volts, assuming the potential drop across it is 0.7. Okay. Also note down the direction of the diode and the clipper and the which part of the waveform it is clipping. In this clipping circuit, the diode is connected like this. It is clipping the positive waveform. We're going to see that when it will be connected the other way, it's going to clip the other waveform. Okay, so let's do the second example now. Okay, so let me do this over here, in which I'm going to have a resistor, and now my diode is connected the other way. And this is my output voltage, resistor, input voltage. So let me draw the VI characteristics again. So this is our transfer characteristics in between input and output. So when I will draw my transfer characteristics, now I will realize that, right, since the diode is connected the other way, so it will become forward bias when so it will remain cut off. It will remain cut off for all until unless, since it is connected the other way, right? So let's say this is minus 0.5 and this is minus 0.7. So it will start to conduct when it will be minus 0.5, and there is going to be a smooth transition in 0.7, minus 0.7, right? Because when these voltages will be negative, minus for this VI, when this will be minus 0.5, then it will become forward biased, right? So it will only conduct in the negative voltages, and there will be a smooth transition in this period of minus 0.5 to 0.7, and there is going to be a linear transfer characteristics in between VI and V0 for all the positive values. So we can see that over here we have a limiter circuit that is limiting the negative waveform, right? So this is limiting the negative waveform. Okay. And another important thing that you can see is the slope over here is 1. Right? The slope over here is 1 since our V0 equals to Vi. Right? Over here V0 equals to Vi, and similarly over here V0 equals to Vi. Alright. So these are a couple of examples of limiter circuits. We're going to do some more, and these are what we call as a single limiter. Now we are going to do another example of a double limiter. Okay, so let's do one more example of a double limiter. Where is okay, so let's do another example of a double limiter circuit. Okay, so in a double limiter, so let me make a resistor. We have this diode connected, and then we have other diode connected. Plus minus V0, let's say D1, D2, or input V from Vi. And now you can see that we have the diode 1 and diode 2 connected. This is kind of a combination of these two circuits that we have seen in the previous example. In one of the case, in this case it was limiting the positive waveform, and in this case it was limiting the negative waveform. So now when we have connected both the diodes in parallel now, so essentially what it will do is it is going to limit both the waveforms, both of the regions, the positive and the negative peaks of the waveform, right? So our transfer characteristics now, let me draw the transfer characteristics. So our transfer characteristics for this waveform, input and output, will be, it's a 0.5, 0.7, minus 0.5, minus 0.7. Okay. So essentially it will go just, sorry, I'm gonna draw it with a red one. Okay, so it will remain here. There's going to be a smooth transition and then constant. There's going to be a smooth transition and then constant, right? And that's it. This is limiting at 0.7 volts and minus 0.7 volts, right? So just by looking at the circuit, we can easily draw the transfer characteristics. So you may see some of these problems often in the book and in your exams or other quizzes, where you can easily draw the transfer characteristics. Okay, and the reasoning is exactly the same over here. When our VI is less than 0.5 volts, our D1 becomes forward biased. When VI is less than 0.5 volts, our D2 becomes forward biased, right? So in this region, this becomes forward bias, and this will start to limit the circuit. And when it is going above over here in this region, this will start to limit the circuit, the positive waveform, right? Okay. So now we are going to do, one more example of this limiter circuit before we wrap up. And that example is how to, we can also design a circuit such that we can define our own limiting values, right? Okay. So defining or designing a threshold for a limiter circuit. Okay, so if you remember, okay, so this was a positive limiter with the diode connected here. Okay, so let's say if I will ask you that I need a 1.4 volt positive limiter, how are you going to design that? All you need is this, and this, right? So there's going to be a potential drop of 0.7 here, potential drop of 0.7 here. So and looking at the connection of the diodes, if I will go back over here, right, you can see that this is going to limit the positive waveform. My output characteristics over here can be simple. Okay, this is going to be constant with a smooth transition, 1.4 volts. Okay, so this is output and this is input. What if I will ask something more different? For example, I want, let's say, again, I want a positive limiter. I want a positive single limiter, right? So I am to define a single, I want a single limiter, which means diode can be connected in just one direction. And I want a positive peak limiter. This means I can connect my diodes like this. Otherwise, it would have been the other way. And then I want the threshold voltage to be, let's suppose, 4.7 volts. Okay, so you can easily make this thing by also, rather than using only the diode, we need a diode to at least define this, to build the limiter circuit. And then whatever extra voltage that we need, what we can do is we can just connect a battery. So I can get a 0.7, I can get a positive limiter, positive peak limiter by the diode in this configuration, and then I know the potential drop over here is going to be 0.7. Now I need another extra 4 volts. So what I'm going to do is I'm going to just connect a battery here. So this battery is going to be 4 volts. This is going to be around 0.7 volts. So my output will be, so if this is VI, this is V naught, my output will be limited, okay, at 4.7 volts. Okay, so with that, so this finishes up our limited example. There is one more example left. I can also have another, which we can do in the next short lecture. All right, with that, thank you so much. I will talk to you in the next lecture. Bye-bye.